Hello everybody. Thank you all for attending our virtual presentation for the Utah Biomedical Engineering Conference today. My name is Sean McKellar and I'm a student in both the electrical engineering and physics programs here at the University of Utah. There's a picture of me in the bottom right-hand corner. I worked with Dr. Cynthia First and Kaitlin Hall in this research, and today I will be presenting on new methods for 3D printing implantable antennas in the human body. I hope you enjoy. Really quick, here's a brief overview of the presentation. I will begin with an introduction, the motivation, and the objectives of our research group, and afterwards I will talk about the particular work that I've done on this project. Antennas are an important part of many implanted medical devices, or IMDs, in use today. Being able to send and receive information or power in an IMD is imperative to the function of the device and the safety of the user. Specific examples of devices that utilize antennas include pacemakers and defibrillators, but there are so many more. As technology gets more advanced, we are seeing these devices get smaller and smaller. Simultaneously, they are sending more data and using more power because of this. Furthermore, the devices are getting so small that built-in antennas are becoming less feasible. There are thousands of patents for new IMDs already in circulation. Specific applications include sensing, drug delivery, and stimulation that are particularly pertinent. One of my personal favorites is shown in the top right. It's a small glucose sensor made for diabetics. With these concepts in mind, we will need new and innovative solutions for the antennas used in the IMDs of the future. What are some of the design constraints we are faced with when designing medical telemetry antennas? Well, in the case of the built-in antennas in the previous slide, the only two constraints are the size and shape of the antenna must fit within the IMD, and the antenna must follow SAR guidelines. In case you've never encountered SAR, it stands for specific absorption rate, and it has the units of watts per kilogram. It essentially tells you how a material absorbs electromagnetic radiation. You can see an image of a SAR distribution in the bottom right-hand corner, where the area of brighter color corresponds with a higher intensity SAR. With implanted antenna design constraints, we face a couple more unique challenges, the first and most important being bioincompatibility. In my mind, this is the only constraint that's really a limiting factor here, and if bioincompatibility wasn't an issue, we would probably see many more implanted antennas as a commonplace thing. The next constraint we face is invasiveness, and this will always be a problem with really any IMD, and it's strongly correlated to the shape of the antenna that we're building. Bioabsorption is going to be another constraint in the case of 3D printed antennas. Typically, when you're 3D printing something, you have to extrude some liquid material. And you'll see with the methods that we present that bioabsorption is going to be a large constraining factor in our design. Lastly, the antenna must follow SAR regulations again. This is going to be more of a concern in the case of an implanted antenna, since it will be in direct contact with the human body. A new method for fabrication of biocompatible antenna. So there exists a biopolymer which is conductive, biocompatible, and it solidifies at 45 degrees Celsius. It was actually also designed by researchers here at the University of Utah, Professor Huan and Zhang. Using a microwave applicator, we can apply heat to this biopolymer and create an extruded antenna. You can see in this visual aid in the bottom corner how this process might work. We think that with this method, we can create antennas made from the biopolymer. If we are able to create an antenna using this biopolymer, it removes bioincompatibility as being an issue with our antenna design. And if bioincompatibility is not an issue, we can take a more conventional approach to our antenna design. Researchers at our institution, Drs. Bernardi, Schurig, and Furs, worked together on a proposed lens antenna design, which could be produced using the method outlined in the previous slide. This is an animated image of the proposed lens antenna simulated in CST. a simulation software that we use pretty extensively. Around the same time period, Kaitlin Hall was working on the design of a microwave applicator antenna, which can be seen here. This is essentially a coaxial antenna with a hollow inner conductor. The hollow inner conductor will allow us to put the biopolymer inside of this antenna, and it should allow us to extrude and 3D print the antennas using the method that we previously talked about. As a proof of concept, Kaitlin Hall went up to the University of Madison, Wisconsin, because they have a high-power amplifier there that worked in the frequency of interest. What they did was they used a coaxial antenna, not the one from the previous slide. Needless to say, they provided a high power of about 15 watts for roughly 20 minutes, and the results can be seen in this slide. You can see that there's a small coagulated region inside the biopolymer vial. This is exactly what we're looking for. Now that I've told you about the long-term goals and aspirations of our research, I'm going to start to go into the specific work that I've done on this research project. Alright, for my work in this research, I was given one main goal: to design a testing platform for microwave heating antennas here at the University of Utah, where my end goal is to be able to take a small vial of the biopolymer and make it solidify using some sort of antenna. Now, because this biopolymer is very expensive, the material that I'll be working with is Eggwhite, since it's cost effective and it behaves quite similar to the biopolymer. I was also given two additional constraints. The system or process that I designed should work at 2.45 gigahertz because it's a commonly used industry scientific medical band, and it should also work with the lowest amount of possible power. The very first thing I had to do was choose and design a microwave heating antenna. I decided to go with a dual slot antenna because all it is a coaxial wire with two slots removed from it. So you can see the simulation that I built over here, and what it is a coaxial wire. So it has a center conductor, a dielectric, and an outer conductor. And then I removed these two slots right here and right here. I also went to the extra step of wrapping this whole thing in a silicone catheter, just because I figured our final design might look a little bit more like that. So from here, I used the simulation software to run an optimizer. And what it did is it essentially changed the location and widths of these slots, and it tried every possible scenario it could think of, and it found the S11 response at that specific design, and it tried to minimize that response at the frequency 2.45 gigahertz. So in case you've never encountered S11 before, all S11 really tells you is the amount of reflected power coming from the device. So for this particular graph, we can see there's a global minimum right here at about 2.25 gigahertz. And at that frequency, we have an S11 value of roughly negative 21 dB. So negative 21 dB ends up giving you about 0.01. So that means that at this frequency, the device is absorbing about 99% of the power sent to it. And at this other frequency, 2.45 gigahertz, it's absorbing a little less. I think it ends up being about 80% of the power sent to this device will be absorbed at this frequency, which isn't bad, and it should, well, I was thinking it should work for our scenario, but we'll get to the results in just a moment. I also included this little animated image here of what the antenna looks like with its electric field. Here I've just included two images of the fabricated antenna. So this image on the left is the same antenna as the one on the right, but this one doesn't have the catheter on. You can also see where I've removed the outer conductor right here and right here. And of course, the size of these slots are as close as possible to the simulation. From there, I went into the lab and measured the S11 response of the antenna. When I was doing this testing, I didn't have egg whites with me, so what I ended up using instead was a solution called human blood bank. Now, human blood bank is going to be very electrically similar to egg whites, and it's a reasonable approximation. So what I did was I connected the antenna here to a coaxial cable, which is fed to something called a vector network analyzer. That's the equipment that is capable of performing the S11 measurements. The results are seen right here. And as you can see, I ended up testing two different antennas. So their values were negative 12.9 and negative 14 at the 2.45 gigahertz. Now we will do a quick side-by-side comparison of the real-world data antennas versus the simulation. And as you can see, the simulation data looks a lot like the real-world data here, but it looks like it's shifted right about 1 gigahertz. So I wasn't entirely sure right off the bat what could be causing this, but I went into the CST simulation software and found that by making small adjustments that would be reasonable for human error, such as sliding the slots down just a millimeter or two, I could actually get these graphs to look very similar. So I think it's reasonable to assume that the differences in these two graphs is really caused by human error. Nonetheless, the effects shouldn't be too different since this is a reasonably low S11 response at that frequency. Afterwards, I tried to perform my first attempt at cooking Eggwhite using my new antennas. So this device here is a signal generator, and it's feeding into a power amplifier. So at this point, this power amplifier uses another power source, and it just adds some power to the signal which is being fed into it. And after that, it feeds it into a power meter so that I could read how much power we were putting into the device. And that's this little blocky device on top. Now, we're still feeding the same signal directly into the antenna here. And the antenna is submerged in egg white. Unfortunately, with the results, I was not able to cook the egg white, but I attribute that to not enough power. We ended up taking these power measurements, which are also in dB, and calculating that we were only delivering 2 watts of power to the device. Over the course of roughly 2 hours, I was able to see the egg white solution rise nearly 10 to 15 degrees Celsius. However, it never seemed to get high enough to actually cook the egg white. All right, from here, there are a couple things that I could do next to move this project along. The first would to be building a more optimized antenna. So I've actually looked at this a little bit, and I've tried, for example, designing a monoslot antenna to see if I could get the S11 response to be lower. But I actually ran into pretty much the same issue where I think the S11 response wasn't really much lower than the case with the dual slot antenna. And so unfortunately, I think we're going to have to build a more complex coaxial antenna in order to make a better antenna. Next up, a solution would be to acquire a new power source. We've looked into purchasing a 10-watt power amplifier like we used up in Madison before. However, it's a bit too expensive, and so other solutions would be to build a magnetron generator or a ham radio transverter. This magnetron generator solution has me particularly excited. What we would do is take the magnetron from a microwave oven, which operates at 2.45 gigahertz, and essentially build a generator with it. I think that'd be really fun. Now, next up in the next couple of weeks, we'll be getting a new antenna shipped in from out of the States actually. And during that time, I'm actually going to perform some dielectric measurements of pork skin over a range of various temperatures and frequencies. And using this, we are going to generate a 3D model of the dielectric constants of the pork skin. I think it's going to be pretty interesting. At this point, I will conclude our presentation and remind the audience that they can contact us with any questions they might have. You can reach me through this email. You can ask them through this Huba conferencing app, or you can join our Zoom session. The information is seen here, and it should also be included in the description of our presentation. Thank you